All right. Good morning, everyone. So it's a short week this week. There's no class on Friday, if I remember correctly, and then there's no class next Monday as well. So we have two shortened weeks in a row. So I guess like what the next couple of weeks are going to look like, or the next 2 weeks are going to look like, is there's only I'll say like three more sections left that we need to cover from section 15. So we should be able to cover those sections throughout this week. So Monday, Tuesday, and Wednesday. And then next week we just have Tuesday, Wednesday, and then Friday will be the day of the exam. So the next exam is Friday of next week. And so that means on Tuesday and Wednesday we're just going to be doing there's going to be like an exam review I'm going to post this week. And then there'll be like a group work as well. It's kind of like a practice exam. So just like the first exam, there'll be resources for studying for the second exam as well that are pretty much the exact same, except the content's going to be different. And so, really, the two major sections that we still have to cover, we have to finish the triple integrals. There's still a couple of examples there. And then we're finally going to be looking in integration for polar, cylindrical, and spherical coordinates. So it's like integration and alternate coordinates. And then if we have time, it's not always guaranteed that we get here. Um, but I might spend time in section 15.6. That's why I was like hesitant in the beginning to say if it's going to be like three sections or two sections. If there's enough time, we'll do change of variables, which focuses on the Jacobian and helps you derive other ways of integrating pretty much. Okay, so we're going to do triple integrals. Does anyone need the notes from last week at all? Yeah, there's only two more problems that we have to do. All right, so we've been doing triple integrals. They're kind of, I mean, maybe they're not so bad. They're kind of annoying in that it's just a lot of work and a lot of writing. But yeah, triple integrals, integrals over three variables, which means that you're integrating over a three-dimensional region. And so we looked at a couple of examples, right? We've done two examples, I should say. We did this example on page 9 here. This is like a good example to know how to do. And that it's illustrating that we're caring about these z-simple regions, which are really just regions bounded between two surfaces. This one and the next example, they were bounded by planes, but it isn't necessarily going to be bounded by planes, as we'll see in the next example. But you just go one integral at a time. So in these examples, we've always been doing like dz, dy, dx, but you can do it in whatever order is most convenient pretty much. So sometimes you'll integrate with respect to y first and then z. It varies from problem to problem. And so again, one thing I want to emphasize before going on to the next example is when you're looking at these kinds of triple integrals, it's like with every integral you compute, so from the innermost to the outermost, you're always losing one variable with respect to the bounds of integration that you have. So this first integral that you compute is in terms of x and y. So that means you're integrating over this three-dimensional region. And then you have this integral from 0 to 1 minus x with respect to y. That means you're integrating over this two-dimensional region. And then lastly, you're doing the integral from 0 to 1 with respect to x, which is integrating over this region. Right, so you're going from three-dimensional to two-dimensional to one-dimensional as you're going from the innermost integral to the outermost integral. So it's something to keep in mind. It's something students make mistakes on the next exam. So I'm saying it over and over again to hopefully reinforce it a little bit more strongly. Okay, so we're gonna go through this example. This one's a little bit more interesting, as you can probably see. Like we're not bounded between two planes. Like we're bounded between kind of like two parabolas. Or I guess you should call them like paraboloids because they're kind of like surfaces that are akin to parabolas. And so we're going to be integrating f of x, y, z is equal to x over the region W, bounded above by z is equal to 4 minus x squared minus y squared. And then it's bounded below by x squared plus 3y squared. And then we're going to be focusing specifically in the octant x, y, and z are greater than or equal to 0. So that means we're just focusing on, at least if you look at this picture, it's like this octant here. So we only care about non-zero, or I should say like non-negative values of x, y, and z. Right, so we're looking at the region bounded below by this parabola and then bounded above, or I should say bounded above by this parabola, bounded below by this parabola, which means we're looking at this region right here, except it's three-dimensional, not two-dimensional. So it's illustrated here, maybe in a way that's a little bit better. And so first we'll integrate with respect to z. And really the more challenging part comes with integrating over x and y. Because we're going to have to be able to describe this region down here. And so first we'll integrate with respect to z because the bounds aren't so bad for this one. So I'm going to write it in the following way. So we have the following triple integral. And this first double integral is going to go over d. So it's some two-dimensional domain. And then inside of this, we have another integral, which is going to be x. So f of x, y, z is equal to x. And then we're integrating with respect to z. And then we have some dA. And so with respect to z, you just follow what the problem tells you, right? So this isn't really the hard part. It's telling we're bounded above by 4 minus x squared minus y squared. So that's the upper bound of integration that we have. And then we're bounded below by x squared plus 3y squared. And so you just integrate this with respect to z. Again, this isn't really the more challenging part. So you take the integral with respect to z. You're going to get an xz. And then we're integrating from x squared plus 3y squared. And you have 4 minus x squared minus y squared. And then you have the dA. And so you plug in for z, this 4 minus x squared minus y squared. And then you subtract by x squared plus 3y squared. And so I'm just going to write out what that ends up being. It's not too hard to write this out, but I'm just going to skip the writing pretty much. And so this is going to end up giving you, so you're going to have like an x times a 4. So you have a 4x. You're going to have like a minus x squared. Minus x squared minus x squared, which is minus 2x squared, and then you multiply by x. That's really going to be minus 2x cubed. And then you have minus y squared minus 3y squared will give you a minus 4y squared. And then you multiply that by x, the x that's right here. And then you have, well, I'm just going to continue writing it as dA for now. We're not going to go into the specifics over, like what we're integrating with respect to d yet. But this is our, I guess, polynomial in two variables, right? So all I did was just integrate with respect to z, plug in these numbers, and you end up getting this function here. And so now what we need to do is we now have a double integral over d, where d is really described by this region right here. It's like this region that we're integrating over projected down onto the xy axis, which is this region here. And then before telling you how to do it or how to set it up, maybe I'll ask you, does anyone have an idea on if we wanted to describe this region here, how might we be able to do that? Like, what should we do? Any ideas? Maybe it's a little unintuitive, but it's similar to something you've done in the past. Like really what we want to do to understand this region here is we really want to be able to describe the intersection of these two surfaces. And then once we find that intersection, we're going to project it downwards onto the XY plane. And that's really going to determine this three-dimensional region here. And again, we only care about the x, y, and z values greater than or equal to 0. So we don't care about like this entire thing. We only care about within like the first quadrant here, or first octant. Well, I guess I could say quadrant because we're restricting down to the xy plane because we're doing the double integral. And so what we're going to do is we're going to find the intersection of these two surfaces. And that'll give us some sort of an equation. Like it looks like it should be the equation of an ellipse, but we should verify that. So we're going to find the intersection. And maybe I'll do it down here. So that way I can have the integration computation kind of as a continuous stream, I suppose. So this is the intersection of the two bounds that we have. So we do 4 minus x squared minus y squared. And then we set it equal to x squared plus 3y squared. And again, we have a bunch of squares that are kind of, you want to combine these terms together, right? We have the x squared and the y squared. We can bring it over to the other side and maybe we'll get something that looks more easy to work with. So this is going to be 4. If I add it over, this is going to be 2x squared and then plus 4y squared. right? So we have this equation here. And what we can do now is, I mean, all this is divisible by 2. So I'm just going to divide everything by 2. If you divide everything by 2, you get 2 is equal to x squared plus 2y squared. And so I'm going to, I mean, maybe it seems like, why did I write it in this way? This gives us an equation of, like, this gives us a way in which we can write x in terms of y, right? Like if we subtracted both sides by 2y squared, this would tell us the following. So if I divided or subtracted over, this would tell us that we have like x squared is equal to 2 minus 2y squared, which implies that x is equal to the square root of 2 minus 2y squared. And again, we know it's plus because we're in the first octant, which means we're only considering values of x, y, and z greater than or equal to 0. So this is going to be plus. But so this gives us a way of relating x with y, but we don't really know, like, where's that actually going to show up. And so I'm going to go a little bit further. So I really just want to describe this region here. And we talked about ellipses in the past, but you can take this equation and go a little bit further by dividing by 2 again. So you get 1 is equal to x squared over 2 plus y squared. And you can rewrite this in the following way. This is really the same thing as x over the square root of 2 squared plus, I'll do y over 1 squared. And I mean, we haven't talked about ellipses too much, but this is the equation of an ellipse now, right? This is an equation of an ellipse from this form here, where the x radius is given by the square root of 2 and the y radius is given by 1. Right, so I'll put that in words and I'm going to draw the picture. So this is the equation of an ellipse. So it's the equation of an ellipse. And I'll just say, it's not like the formal language, but I'm going to say x radius given by the square root of 2. And then y radius is given by 1. So it looks something like this. Maybe it'll be better if I draw a picture rather than putting into words. So we go over the square root of 2 units with respect to x, and then you have like the minus 2 square root of 2 with respect to y, the other side of x. I was going to say y, that's not right. And then you have 1 and then minus 1. That's what I mean by like x radius square root of 2, y radius 1. And so if you draw this, it's not going to be perfect, but it should be like an oval, like so. And then we're only caring about the first quadrant. We only care about values of x and y that are greater than or equal to 0. So this is our region D right here. Right, so this is the region D. And that's exactly what they have described here. I'll scroll back down. But if you compare this picture with this one, it's the exact same. Except in this picture, they have more detail, right? But we are able to describe this region right here. And then we also know how to describe x in terms of y from this equation that we had here. And so now we really know how to set things up, right? So with respect to x, we're going from x is equal to 0 to x is equal to the square root of 2 minus 2y squared. That's this curve right here. And then with respect to y, we're just going from 0 to 1, right? And so if I go back up to the integral computation, this is going to be equal to the following double integral of 4x minus 2x cubed minus, I'm going to change the order of x and y because I like x before y. And then this is going to be, so with respect to, like, we have x as a function of y, like we're thinking in terms of this being horizontally simple. So we're going to integrate with respect to x, and then we'll integrate with respect to y. So this is going to be dx, and then this is going to be dy. And then with respect to x, we're going from 0 to the square root of 2 minus 2y squared. Again, that's this equation, really describing the ellipse. And then with respect to y, again, we're going from 0 to 1. So that's kind of the hard part of this problem, is this setting up the double integral, because they kind of told us what the bounds were going to be for z, so we didn't have to do a lot of work there. And then, I mean, from here, if this were an exam problem, I would allow you to just stop right here. But I'm going to show you what the answer ends up being with maybe a smaller amount of detail. So you would integrate with respect to y, or integrate with respect to x. I mean, so if you integrate with respect to x, this is going to become the integral from 0 to 1. This is going to become 2x squared. So you're going to get 2x squared. You get a minus 1/2 of x to the 4th power. And then this is going to be minus 2x squared y squared. And then you'll have a dy. This is going from 0 to the square root of 2 minus 2y squared. Right, so that's just the integral of this with respect to x would give you this function here. When you plug in the square root of 2 minus 2y squared, I'll just write out what that ends up being equal to. This ends up being equal to 2x squared. Oh, I'm writing out the wrong thing. This ends up being equal to 2 minus 4y squared plus 2y to the 4th power dy. And then if you integrate this, I'll just show you what the answer ends up being. So you integrate with respect to y, just like you would in single variable calculus. You plug in y is equal to 1. It ends up being equal to 16 over 15. So maybe I'm skipping a step in finding the antiderivative, but I'm assuming that you're comfortable finding this antiderivative of a polynomial. Right, so again, the hard part is setting things up. On the exam, because this part's kind of so annoying where you have to like plug in the function and then do some subtraction. Usually on the exam for these kinds of problems, I'm just going to ask you to set it up without completing the computation. Just because I assume you know how to do, I don't know, like integrals or integration, finding antiderivatives. Like there will be a problem where you have to go through with the whole computation, but it'll be faster. For these ones where it's more annoying, you just have to set things up. Like this would be what I would be asking for on like an exam. Okay. Any questions about this example? Yeah, if you know how to do this one, I think you're in pretty good shoes. And that I'm not going to really ask a problem on the exam that's harder than this one for setting things up, I would say. Not to say it won't be different, but it's kind of, I don't know, it won't be that much more difficult, or it's probably going to be a little bit easier, I would say. So the last thing I wanted to talk about before going into 15.4 is there's this problem on average values. We talked about average values with respect to single variable and double. Well, oh yeah, there's like an Amber Alert that went out. It's distracted me. But yeah, so we talked about average values with respect to single variable and double variable. Sorry, I'm like, I need to get back on track thinking. And now we're going to do it for 3 variables as well. So the idea is going to generalize in the sense that the average value is really just going to be, now it's the triple integral over your like triple variable function. And now instead of dividing by like the length of your interval or like the area of your domain, it's now going to be the volume of the region. So we're now dividing by the volume instead. Where again, usually it's hard to remember a bunch of volume equations, and sometimes it's just not going to be, I don't know, sometimes volume can be really difficult to compute. You can remember, this is like something good to remember, is that you can always write out the volume as being the triple integral of 1 evaluated over W. So if you want to find the volume of W, it's just the triple integral over W of 1, which isn't so bad. Right, and so this is similar. I don't know if I really want to do this, but it's similar to what we were doing. Oh wait, no, it would have been, actually I don't even remember where we did the average. Oh yeah, it's similar to what we were doing on page 5 of the notes, right? So this was single variable, this was double variable. So this is like length of the interval, area over the region, and now we do the volume. I kind of went over this whole spiel when I first introduced it, so I won't say that much more. So we'll just go through an example. And this one, I'm maybe going to just, the integral itself isn't that interesting, but maybe I'll just set things up and then kind of speed through the computation so we can get to polar coordinates. And so for this example, we're told we have a solid piece of crystal W in the first octant of space that ends up being bounded by the 5 planes given by z is equal to 0, y is equal to 0, and x is equal to 0. So for x, y, and z, before going further, so we have x, we have y, we have z. We have all of these are bounded below by 0. That's what it just told us. Maybe I should give more space here. So they're all bounded below by 0. And then there's two other planes it's bounded by. It's bounded also by x plus z is equal to 1. And then x plus y plus z is equal to 3. And so there's going to be problems like this in the future. And there's kind of like a way of thinking about things that maybe isn't completely formal, but is how I think about things. And so if you look at these two planes that it gives you, it tells you that x plus z is equal to 1. So there's a way of expressing x and z in terms of a constant amongst just like two variables here. But the only way to describe y is in terms of x and z. And so what this is telling you, based on what I've been saying over the today and I guess the last time we talked about triple integrals, is the innermost integral should be in terms of two other variables. And the only one that's described in two other variables is y here, because you can describe x and z using this equation. So we should be using this equation to describe y, is kind of what I'm getting at. And so if we have x plus y plus z is equal to 3, if we want to write things in terms of y, you just subtract x and y, or x and z, which is going to tell you that y is equal to 3 minus x minus z. That's going to be the upper bound with respect to y. You're going to have 3 minus x minus z. And maybe it'll make more sense why I'm writing it this way after I write out what the integral actually looks like. And then with respect to x and z, we have this equation here, which I'm going to use to express z in terms of x. So if I took this equation and subtracted both sides by x, would have z is bounded above by 1 minus x. And then the last thing we need to know is that we know that z is bounded below by 0. And we also have this 1 minus x here. So we can't have that x is greater than 1. If x were greater than 1, then you'll have like 0 is less than or equal to z is less than some negative number, which doesn't make any sense. Which means that x has to be bounded above by 1. X can't go above 1, otherwise this gets messed up. Right, so if we want to find the average value, the first thing we're going to do is we're going to find the volume, which is this the integral of 1 over w. So we have that the volume, this is equal to the following triple integral. So this is just over 1. And then you have dv. And so in terms of the order in which we're going to integrate, again, we should be thinking the most variables, like the bounds with the most variables will be in the innermost integral. So that's going to correspond to y. So with respect to y, we're going to integrate from 0 to 3 minus x minus z. And then we're going to integrate with respect to z because we have a variable here. So we're going from 2 to 1 and then to 0 variables. So this is going to go from 0 to 1 minus x. And then with respect to x, we're going from 0 to 1. And then instead of writing dv, I'm going to replace it. So we're going from dy to dz to dx. Right? So again, two variables, one variable, 0 variables. Like with every integral you pass, you're losing variables, which tells you you're going from 3 dimensions to 1 dimension. So then you just integrate this thing. It's not really a interesting integral at all. So if you integrate with respect to y and then you plug in, you're just going to get y and then you plug in 3 minus x minus z in for y. So this will become the double integral from 0 to 1, 0 to 1 minus x, and then you have 3 minus x minus z, dz, dx. And then you integrate with respect to z. And so this is going to give you the integral from 0 to 1 of 3z minus xz minus 1/2 of z squared. This is going from 0 to 1 minus x. Let me move this over a little. I'm not going to be able to do it without moving the zeros, but I can move them back. Okay. Right, so you get something like this, and you would plug in 1 minus x And then, I mean, that's going to give you a polynomial in terms of x, then you integrate from 0 to 1. I'll just tell you that this ends up being equal to 7 over 6, right? The actual computation of the integrals is it's a little bit tedious. So I'll just say, like, you end up getting a polynomial in terms of x, and you integrate it, and you plug in x is equal to 1. When I post the solutions, I'll write more detail in case you're curious. But again, I'm assuming you're comfortable doing these like single variable integrals from Calc 1. So that's the volume. We only computed this part so far. So I always want to skip this problem because you pretty much just do the exact same thing over again, except now you have to do it to your actual function f of x, y, z, where the function we're given is just given by x right here. And so we have that the average value, again, this is equal to 1 over the volume, which we just computed. And then this is going to be times the triple integral. The function we're given, we want to find the average temperature. The function is given by x, right? That's the function that was given to us. And then nothing else really changes in terms of how we're integrating this. So it's still going to be dy, dz, dx, where we have that y ranges from 0 to 3 minus x minus z. Y ranges from 0 to 1 minus x. X ranges from 0 to 1. And so we found that this volume was equal to 7 over 6. That's what we computed here, was the volume. So you divide by 7 over 6, which is really the same as just having 6 over 7, but I'm just going to write it as 1. And then 7 over 6. And then, I mean, maybe I won't go into that much detail with the actual computation of the integral. So you do 0 to 1 minus x, 0 to 1. If you integrate with respect to y, you get x times y, and then you plug in 3 minus x minus z. So it's going to end up being 3x minus x squared minus cx. And then you have dz dx. And then from here, you integrate with respect to z. So I'm not going to write out the full detail here, but I'm going to kind of do what I did last time, I guess. So you integrate with respect to z. So you get 3, let's have the alphabetical order, 3xc minus x squared times z. And then you're going to have a minus, I guess, x times z squared. And then it's going to be over 2. And then this is going from 0 to 1 minus x. And then you have dx. And I realized I forgot to have the 1 over the 7 over 6. Right. And so I'm going to kind of skip steps again, just because this part's really not interesting all that much. And so what you end up getting is that this is going to end up being equal. So you skip a couple of steps. Again, I'll fill in the details in the solutions that I'll post later today. But if you calculate this integral to completion, it's going to end up giving you a 3 over 8. And then you're dividing by the average value, which was 7 over 6. And so this ends up being equal to 9 over 28 degrees Celsius. This is the average temperature within the crystal. Right, so I skipped some steps with respect to calculating the integrals, but it's not really the interesting part here. Like, I assume you're comfortable computing integrals at this point. I mean, not to say like you won't make mistakes every now and then with like plugging in the numbers and getting the right thing, but the process, I'm assuming you're pretty comfortable with. Okay. Any questions about this example? Okay. Yeah, so we're going to be moving on from this section to 15.4. These ones are a little bit nicer or a little bit more interesting. And I feel like I'm always like kind of skipping ahead with like these like or these like triple integrals because there's just so much writing that you have to do. And a lot of it's not super interesting, but this one's more about like, this is going to be focusing less on like doing really hard integrals or long integrals instead of like that makes it a little bit better. Okay, I'm not even looking at the right thing. Yeah, so we're gonna finally, I guess this is the main reason why I started talking about like polar coordinates, cylindrical coordinates, and spherical coordinates earlier in the semester. It's gonna make integration over specific regions a lot easier. Again, when you think about polar coordinates, you should be thinking it's like over a circle or like something that's circular, or it could be like an oval or something like that. So before going into this section, this is also something people get confused about that I want to oh yeah, it's like I think the same one or one that's similar. So like polar coordinates, when you're thinking about polar coordinates, you're thinking in terms of circles. Circles are two-dimensional, or at least they exist on like the 2D plane. So this should be like a double integral. Whereas cylinders and sphericals, these are three-dimensional regions. And so when you do cylindrical and spherical coordinates, it's always going to be a triple integral. So this is something to remember. I feel like it's something students get confused about, but it should make intuitive sense, right? If you're doing, like if you're integrating over a plane or like a surface, use the double integral. If it's a three-dimensional region, you do the triple integral. Okay, and so this is going to be in line with what you've been doing in calculus so far with integration, where you do some sort of substitution that makes your integrals easier. So in the past, you've done u substitution, you've done integration by parts, you've done trig substitution, stuff like that. But now we're going to be doing substitution via like polar coordinates. So like x is equal to r cosine theta, y is equal to r sine theta. And in general, I feel like this is going to be pretty intuitive in terms of how the substitution works, aside from one component that you need to remember. And so these polar coordinates are convenient when the domain of integration is an angular sector, or what's called a polar rectangle. So it's kind of like a segment that exists between two circles of different radii. And so there's two parameters we care about. We care about like a change of angle, which is kind of going from a point here to a point here. That means like you're letting the angle increase. And then we also care about a change in radius, which is kind of like this part right here, right? You're going from something of radius 1, really a circle of radius 1, to a circle of radius 2. So if you change the angle and you change the radius, and you consider all angles and radii between those two values, you end up getting a shape that looks like this, which is called a polar rectangle. So that's kind of the basic sort of object we'll see when integrating in polar coordinates. And so we assume throughout that our radius is going to be greater than or equal to 0. And then we also recall that when we're doing polar coordinates, we have x is equal to r cosine theta and y is equal to r sine theta. And so if we're going from a double integral with respect to x and y to an integral in terms of r and theta, there's kind of a part of that makes sense. So if we're looking at f of xy, it's going to become f of r cosine theta, r sine theta. So it's just making a direct substitution. And then we have like radius 1 to radius 2, theta 1 to theta 2. So those are the bounds of integration. So that's specifically looking at these bounds that we have here. The only thing that's a little unintuitive is when we go from rectangular coordinates to polar coordinates, we go from dA to r dr d theta. And so whenever you're doing polar coordinates, you're always going to have an r that's going to show up. And so the question is, where's this r coming from? And so we're going to have two perspectives, one that's a little harder than the other. So we're going to do the hard one first, and then in section 15.6, we'll look at the Jacobian, which gives you another way of coming up with where this r is going to come from. And so where this r dr d theta is coming from is really just estimating the change in area of a smaller polar rectangle, which is shown in the figure on the next page. Right, so if we make an infinitesimal change with respect to theta and with respect to r, we end up getting a tiny polar rectangle like so. And if you make it so the change is small enough, this polar rectangle is going to have an area that's approximately just equal to a rectangle, where the rectangle is going to have side lengths given by the change in r multiplied by this length right here, where this length here is an arc of length given by r delta theta, right? So we have this change in area that occurs with infinitesimal changes of r and theta, ends up being approximately equal to the area of a rectangle with these side lengths, which is r delta theta. And then you can go through this whole Riemann sum process by decomposing the rectangle into a smaller grid of these polar rectangles. And what you end up finding is that this double integral in terms of dx dy is approximately equal to this term right here, where this area is approximately going to be equal to some radius multiplied by delta r delta theta. This is kind of the unintuitive way, or like the more conceptual way of thinking about it. We have a more concrete way of deriving this formula in the next section. So if you don't understand exactly what's going on now, it's not really that big of a deal yet. But again, we're just approximating the change in area when we increment r and theta, which changes dr to this r dr d theta, or r delta theta. So this is the equation for double integrals in polar coordinates. So for a continuous function f on the domain where theta ranges from theta 1 to theta 2, and r ranges from r1 theta to r2 theta. So here they're assuming r is a function of theta, which isn't always going to be the case, but I guess they're writing it out for convenience sake. So we end up getting the following. So if you have this double integral with respect to x and y, and you want to convert it to polar coordinates, you change x and y to r cosine theta, r sine theta, and then you change this dA to r dr d theta. And then you have the balance for r and theta. So this is one of those things where it's just good to work through examples pretty much to develop an understanding versus what I'm saying conceptually here. The first example I want to go through is actually going to be at the top of page 3. So this example should be familiar, and that we did this one at the end of section 15.2. Let me rewrite this. So we did this problem at the end of section 15.2. It was kind of a challenging problem, or at least it was longer. Let me actually show you the example or what I'm talking about. It's this example right here, right? We wanted to evaluate the double integral of x dA for kind of this like half annulus that we found. And there's a lot of writing, right? And there was some trickery involved as well, where we had to integrate over 2 different regions and then subtract the 2 together, which made things a little bit difficult. And so I kind of wrote before that this is an advertisement for polar coordinates, and we'll see why now. And so if we wanted to integrate this region with respect to polar coordinates, so first I'm just going to write it out in terms of x and y, so and rectangular coordinates. So we have x dA over this region D. And so we want to describe this region in terms of polar coordinates. And so how you can think about this region is that this region here is bounded between a circle of radius 1 and a circle of radius 2. And so what that's going to tell us is that our radius is bounded between 1 and 2. Right, so again, you're thinking in terms of circles with polar coordinates. We're bounded between a circle of radius 1 and a circle of radius 2. So r is bounded between 1 and 2. And then we also need to describe the angle, or so like the range of values the angle takes. So we can think about this as starting at minus pi over 2 here. And then you're rotating until you hit the y-axis, which is at pi over 2. And so this is telling you that theta ranges from minus pi over 2 to pi over 2. And so those are going to be the bounds of integration that we have. So in terms of polar coordinates, this is going to be equal to the double integral. So x becomes r cosine theta. So x is going to become r cosine theta. And then dA becomes dr, or it becomes r dr d theta. So dA always just becomes r dr d theta from what we were discussing before. So again, this is, I don't know, this is the part people get confused about. So I'm just going to write this is what dA becomes. This is what x becomes. Right, so these are the same integral at the end of the day. And then we have r goes from 1 to 2. So the radius goes from 1 to 2. And then the angle goes from minus pi over 2 to pi over 2. And now it's just a matter of integrating this. So I could rewrite this in the following way, I guess, before integrating. So this is going from 1 to 2 minus pi over 2 to pi over 2. And then we have r times r. That's going to give you an r squared. So you have r squared cosine theta dr d theta. And at this point, it doesn't matter the way you integrate it. You can do the integral with respect to theta and then r or whatever. We're going to integrate with respect to r. So r is treated as the variable, which means that this is just going to become r cubed over 3. So this is going to be equal to the integral from minus pi over 2 to pi over 2. And you have r cubed over 3 cosine theta, where r is going from 1 to 2 d theta. So you plug in r is equal to 2. That's going to give you 2 cubed, which is equal to 8. And then you subtract by what you get when you plug in 1. So you have 8 over 3 minus 1 over 3, which will give you a 7 over 3. So this ends up being equal to 7 over 3 times the integral from minus pi over 2 to pi over 2. And then you're left with cosine theta d theta. So the antiderivative of cosine is just equal to sine, right? The derivative of sine is equal to cosine, so antiderivative is just equal to sine. Sorry, my pen's driving me a little crazy. Okay, this is 7 over 3, and then this is going to be sine theta going from minus pi over 2 to pi over 2. If you plug in pi over 2, you get 1, and then you subtract by sine of minus pi over 2. Sine of minus pi over 2 is equal to minus 1, so you get 1 minus minus 1, which gives you 2. So this ends up being equal to 7 over 3 times 2, which is equal to 14 over 3. And that should agree with the answer that we had from last week, right? So we got 14 over 3 here, and that's exactly what we found before. The integral ends up being equal to 14 over 3. Except there's much less work done in polar coordinates than what we had to do over here, right? So you get the same integral with like 1/4 of the amount of work, right? So you can do this a lot faster. I mean, I spent a lot of time explaining it because it's the first polar coordinate example we did, but in the future, once you get enough practice, you can do a problem like this in like 2 to 3 minutes or so. I guess depending on your pace. Right, so that's what's going on with the polar coordinate. Any questions about this example at all? Yeah, question.
R sine theta instead of r cosine.
If you have a y that shows up, maybe let's see, is this next one, like this next example, there's going to be like an r sine theta that shows up. Like if so we only had r cosine theta just because we were only integrating x, so we get r cosine theta just using this substitution here. Does that make sense? Yeah, any other questions before the next example?
Like all the tests, can we like evaluate the integral of the calculator?
You should show your work. Yeah, the point is, well, I guess, well, I need to make sure you know how to do like double integrals and like, well, I guess you're only allowed to have like a scientific calculator on the exam anyway, so like you're not going to be able to have like a calculator that does integral problems. So yeah, but yeah, I mean, you're probably gonna have to do like actually compute like one integral on the exam. Don't quote me on that. It's 1 or 2, but there's usually like one problem that's like pretty simple where I give you a double integral just to make sure you know how to do like the process of like the iterated integrals. But the other ones are mostly just going to be set up and not focusing on going through with the computation. Any other questions about this one? Okay. Yeah, and so I want to go up to the one above. This is the one I usually start with, but I wanted to emphasize that we're just doing the same thing as we were doing before, except in a way that's a lot easier. So for this example, we're doing the integral of x plus y. And it's pretty much the same idea over again. So we want to think about our bounds in terms of r and theta. I mean, this kind of looks like a circle, just like cut off a little bit. So it's kind of your intuition for using polar coordinates. And so the bounds here with respect to r, we're going from a circle of radius 2 to a circle of radius 4. So that means in terms of r, we're going to be bounded between 2 and 4. And then with respect to theta, we're starting on the x-axis and then going to the y-axis. So that means that our theta is going to range from 0 to pi over 2. Right, so theta is just going to range from 0 to pi over 2. I don't know. I feel like people really don't like the polar coordinates, but once you get used to it, it's not so bad. So this is 0 to pi over 2. And then in terms of what we're actually integrating, so if we have this double integral of x plus y dA, if we're writing it in terms of polar coordinates, you have this double integral. R ranges from 2 to 4. Theta ranges from 0 to pi over 2. And then we have x plus y. So x becomes r cosine theta. Y becomes r sine theta. So this is one example where r sine theta shows up. So this is x plus y. And then the dA becomes r dr d theta. So this part is x plus y. This part is dA. So again, they're the same integral over again, just written in terms of r and theta. And so you can rewrite this in the following way. You can factor out an r here and then multiply it by r, which will give you an r squared. So this is really the double integral from 0 to pi over 2, and then from 2 to 4. And then you're just going to have an r squared. And then you have, this is times cosine theta plus sine theta. And then you have dr d theta. And then you integrate with respect to r. So I mean, at this point, it's kind of just, it's pretty formulaic at this point. So you integrate with respect to r will give you a 1 over 3 r cubed. This can be 0 to pi over 2. Get r cubed over 3. Cosine theta plus sine theta. This goes from 2 to 4. And then this is going to be d theta. And so if you plug in 4, you get 4 cubed, which will be equal to 64. And then you have like the minus 8 over 3. So I'll give you a 56 over 3. So this is equal to 56 over 3. You have the integral from 0 to pi over 2. And you have cosine theta plus sine theta d theta. And then here, I mean, the integral of cosine is just going to be sine. The integral of sine is equal to minus cosine. So this is going to be equal to 56 over 3. Then you have sine theta minus cosine theta. Cosine theta. And then this is going from 0 to pi over 2. So if you plug in pi over 2 here, this is going to give you a 1 and then minus 0. And then when you plug in 0, this will give you a 0, and then you'll have like a minus 1. So you really have 1 minus 1. So that would be a 2. So you're really just multiplying the 56 by 2. And so this is going to be equal to 112 over 3. Right. So I mean, people generally don't like polar coordinates, but you can see it really isn't so bad. Like once you make the transformation and you understand like what you're integrating, it really isn't so bad. It's just like any other integral. Right. So we'll continue here tomorrow. If you have any questions, I'll be up here for the next couple of minutes. Okay, thank you. Okay, that's fine. Thank you. Thank you.